Okay. So, the first one, it says the anatomy of the sun. Basically, I think you have 3 internal layers and 3 external layers. And I just kind of brought that figure in to remind you, so you'll need to look those up. But the internal ones are the core, and then you have the radiative zone and the convection zone. It's all in that little figure. And then the 3 external ones are the photosphere, the chromosphere, and the corona. So I think you had a homework question like that.
Yes, we did.
Good. So if you want to put homework question, that's kind of what it is too. And then I also in green reminded you one more thing. There's that solar wind. So then it says the flight of energy from the core, and I put that in purple. Basically, of course, the energy is created only in the core of a star, or their sun is where the energy is created. And then after it's created, it has this random walk through the radiation or the radiative zone, and it takes about 1,000 years or 100,000 years for it to find its way. And then it has, I said, just through the convection zone, and then through the from the surface of the sun, which is called the photosphere, to the Earth, it just takes about 8 minutes. I think that is so cool.
What was that, Brad?
What's that?
What is that? What zone?
The convection zone above the photosphere.
No.
A random walk through the radiation zone.
Relation.
Yeah. And then the next one, actually, I just brought in that figure from your expert from your textbook. So what's happening with nuclear fusion? You have 4 protons in, and then what comes out is a helium nucleus, 2 gamma rays, that's your energy, and then 2 positrons and 2 neutrinos. And then, like on the slides, I said the mass that you're lost is about 0.7% of the original mass, and that's what's converted to energy. And I think you had a homework question for the next one, too. Gravitational equilibrium, and I brought this figure from your textbook. That's a balance between gravity and the sun's energy pushing outward. And then sun's built-in thermostat. That was that complicated figure. It kind of looked like this. Where basically in red I say the sun cools and then it contracts. And because it contracts, it heats up, basically. Oh, sorry, it cools, it contracts. Yep, so it basically kind of corrects itself. And then the next one, neutrinos. I just kind of refer to up there in green, neutrinos. They're elusive, means they're hard to find or hard to track, but because they pass through matter. But and then the sunspot cycle. The cycle's about 11 years, and the sunspot cycle is created because of the sun's magnetic field lines. Mm-hmm. And so I kind of showed him playing Twister down here, kind of the 3 suns twisting, or 3 figures of the sun twisting around. That other little figure then to the right is showing you basically kind of how the magnetic field comes out of one sunspot into another. Then at the bottom in blue I said when the sun is active, you get sunspots. What else did I say? Sunspots, solar flares, coronal holes, coronal mass ejections, filaments, and prominences. And this actually I'm going to post under Doc Sharing too, like usual. That's chapter 11. And like you said, chapter 14 is the doozy right now. So chapter 12 looks like this, where we talked about just kind of stars in general. We talked about luminosity. That's how much energy a sun's putting out per second. It's watts. Apparent brightness is... we use the variable lowercase m for apparent brightness, and it's how bright the object appears, and we can get apparent brightness from E is equal to luminosity divided by 4 pi distance squared.
Luminosity the energy, the stars, all of them, not just the sun, but all of them.
Will you,
Luminosity, because the sun puts the brightness out.
yeah,
So,
I think so.
okay. So, otherwise I got it wrong, because I thought it was, luminosity was kind of like the parent brightness, but it's what it projects, luminosity is what it projects to us, the Earth.
Okay.
So
That sounds like apparent brightness is what we get from it.
Okay.
Yeah. So this might help. So
Okay, then okay. They were so close.
they are.
I probably got it right.
I think
I'm
you
getting it
probably.
mixed up in my head.
It's
Okay.
easy to do.
Okay.
It's really easy to do. Absolute magnitude, we said, oh, sorry, there's just a little bit more with apparent brightness. So apparent brightness scale, remember the smaller the number, the brighter the star or object. You can even have negative, and they're really bright. And then what's the dimmest object on the apparent brightness scale that you can see, can be seen with naked eye, and that's generally magnitude 6, so m is equal to +6. That's the dimmest. And then absolute magnitude. So in absolute magnitude, we're basically, that's when we move the star 10 parsecs from us and see how bright it is. That's absolute magnitude. So put it 10 parsecs away, see how bright it is. And absolute magnitude relates directly to luminosity. And then we get to the 7 spectral type, and that is the O be a fine guy kiss me, where O is the hottest and M is the coolest. But make sure.
O is bluest. And
Right.
M is the reddest.
You got it. Very good. Just make sure, hint, hint, that if I ask you on the test, what is the order from, this is from hottest to coolest. What if I ask you the order from coolest to hottest? You put M, K, G, F, A, B, O. I'm not saying I would do that, but from coolest to hottest, yeah. So binary stars, like the companions, okay, there's 3 ways to tell that you have binary stars. One is if they're visually, if you can actually see them, can visually see 2 stars. The other one is spectroscopic, and I have that little figure there. Spectroscopic uses the Doppler effect in spectral lines. And the last one is eclipsing. So if you have a pair of stars that actually one goes in front of the other one, so a star moves in front of each other to give you different amounts of light, and you know you got 2. That's eclipsing. Then we have several stuff with HR diagrams. So here's my little HR diagram down there. And we've been kind of talking about how the stars kind of line up this diagonal here. Those are main sequence. And then I just kind of call this the 2. I just generally call those giants. And then 3 are your white dwarfs. But you probably would be helpful for you to kind of know what an HR diagram, how the plot is set up. And it's set up with putting temperature along the x-axis and putting luminosity along the y-axis. Let's see the next one. Main sequence stars. Main sequence stars are fusing hydrogen into helium in the core. And then what I did with that blue line there that says high mass to low mass, actually that is supposed to, this line right here is really this line right here. Okay, that kind of diagonal, that's these stars right here.
Okay.
And these are high mass and these are low mass. Then I said, actually, you know, how would you compare, and it's kind of like what you were just saying, the color of a low mass is going to be red, the color of a high mass is going to be blue, the luminosity, that's L, capital L, of a low mass would be low, And the high mass would be high luminosity, cool, and hot.
Okay.
So, and then clusters of stars, all born about the same time. We have open clusters and globular clusters. And globular clusters, the stars are old, and it's like a ball of stars, and they're located in the halo of our galaxy. But open clusters tend to be younger, they're kind of spread out instead of a ball, and they're actually, open clusters are located in the disk of our galaxy.
So that's it. We could just check our homework on that one.
What's that?
Our homework question on that one.
Yeah. And then the last one, HR diagrams again, clusters of stars. I'm looking for turn-off points. So here's a figure from your textbook, and I don't know if you can see the purple, the blue, kind of the yellow. Those are all different clusters of stars. And we said that the massive stars age faster, so they actually turn off they get used up before the low mass stars. So you kind of have this effect where you can see where the turn-off point where most massive star left on the main sequence. Where is the most massive star left on the main sequence? That's like the top of the diagonal. That's your turn-off point. And more massive stars have left the main sequence. That's a way of aging. I think I might add that. Maybe I should add that. So I'll put it in purple over here. This so you're able to tell or understand the age of star cluster.
When you say have left, does that mean they have died?
Yeah, they have left
Okay.
because they've left the main sequence. Yep,
Right.
yep, they have
kinda
died,
like
so to speak.
burn out.
Yeah, but remember they don't
Right.
last very long. They're like red giants for a little while,
Right.
and then they either blow up or they. But yeah,
I was reading somewhere where when they blow up, it's like 100 atom bombs or something.
that could be a lot of energy.
Or not 100, 100,000 atom bombs or something like that. 100,000 atom bombs or something.
Mm-hmm.
There's a lot.
It's a lot of energy.
Yeah.
So the next term, molecular cloud, they call it stellar nursery. That's where a bunch of stars can be born at the same time. I just said especially large nebula, where multiple stars can be born. And the next one, protostar. I think I'll put protostar is shouldn't be a baby star because protostar. I just guess I should maybe say a pre-star. Yeah. Okay, and then a protostar will keep collapsing and it will stop collapsing when it begins fusion in its core, hydrogen fusion, and that's when it's a main sequence star. Main sequence star is what our sun is doing, a main sequence star, and it's fusing hydrogen and helium. And this stage lasts the longest. Oh my gosh, painfully long. And then planetary nebula is when the dying star ejects material into kind of like a shell-looking. And I kind of put in green in a planetary nebula, somewhere lurking in there is a white dwarf. And then the reason that we have stars either blow up or turn into white dwarfs actually just all has to do with their mass, because of the different masses. The more massive the star is, the faster it's going to age. We must have we talked about brown dwarfs before, didn't we?
Yes, we did. That's what I was like. I didn't hear much about that guy. They were mentioned it in a book and then on the movie.
The video, yeah, the movie. So brown dwarfs are the failed stars. They glow for a while, but they didn't ever begin fusion. So they have less mass than 0.08 solar masses. And then helium fusion occurs in the core after hydrogen fusion. I think I'm going to add to that. Occurs in the core of hydrogen fusion in giant stage. And then I also said helium fusion creates carbon. All right. Next chapter. So actually what I did was chapter 14 was so long, I went ahead and put it onto 2 slides.
Okay.
So this is the first of 2. We just talked about this stuff. So the white dwarf supernova looks like this. WD stands for white dwarf, and of course there's its giant companion. And then there's the material dropping from the companion onto the white dwarf. The white dwarf picks up mass to about 1.4 solar masses, and then it begins fusion again in its core. It uses carbon, and that fusion doesn't go well. It just doesn't have the bulk to control the fusion. And so the WD, the white dwarf, blows up. Sad face. And then a massive star supernova is different. That would be the type 2 supernova. But the massive star supernova, that we talked about tonight too, I think a little bit. Basically, it ends up with an iron core, and then iron can't fuse. So the core stiffens, and the outer part of the star is blown away. But it leaves a little nubbin that is either a neutron star or a black hole after the supernova event. Red giants, see, it seems like this should have been in the previous chapter, I'm not sure, chapter 13, but red giants are no longer fusing hydrogen in the core. White dwarfs, what did I put for white dwarfs? Are dead, relatively low mass stars. They are basically an orb of carbon. Chandrasekhar limit, that's the one associated with white dwarfs. And that basically Chandrasekhar limit is 1.4 solar masses. And it's a maximum temperature, or it's a mass at which, if you go beyond that mass, then normal degeneracy pressure does not work. Accretion disk. There's a picture of an accretion disk. Of course, that's the accretion disk, kind of that frisbee-looking thing around the retired white dwarf or neutron star. So I put down here, accretion disk is material waiting to fall in towards the center, whether that center is a white dwarf or a neutron star or black hole. Nova events, those also are with white dwarfs. Okay, but in the case of a nova, the white dwarf does not blow up. Just simply it gets enough fresh hydrogen to begin a little bit of nuclear fusion. And the cool thing about nova events is that the white dwarf is left intact. So these can reoccur. And then gravitational redshift, actually I say something here and then I say something in the next one. This is very wordy, my gravitational redshift, so get ready. Basically I said objects with extreme gravity, such as neutron stars or vicinity of black holes, steal some of the energy from light, making it longer wavelength. And the example I have on the next slide is the spaceship. Remember we sent kind of we stayed orbiting, but we sent something closer to the black hole, and its numbers turn red. That's gravitational redshift. So it looks like this, gravitational redshift in action right there. Then we're almost done. Neutron star. It's one of the two outcomes from a massive star going supernova. And then I put that protons combine with electrons to form neutrons. And a pulsar is the indication of a presence of a neutron star. So a pulsar is the signature of the presence of a neutron star. And here's kind of the figures from your textbook, how that works. And how does a black hole from a stellar black hole form? So in that case, basically, it doesn't stop at a neutron star. Basically, neutron degeneracy can't support it. I think we said 3 solar masses or more, didn't we? I think I'll add that to it. I'm going to put greater than 3 solar masses. And that ends up being like 25 solar masses. That's the main sequence star. So then the problem is kind of the fabric of space and time collapsing on itself in the vicinity of the singularity. Speaking of, the anatomy of a black hole is kind of what I drew tonight. The middle of a black hole is called singularity. Then it actually has an event horizon, and that's kind of the place where if you're on the inside of the event horizon, you can't escape. If you're on the outside of the event horizon, you have a fighting chance. Light can escape. Then the Schwarzschild radius is kind of that distance there. Black hole effect, falling into a black hole. So we saw, and we kind of talked about a couple different scenarios tonight, but basically, from an outside observer watching you fall, the outside observer would see your time slow down. Actually, with regard to length, and we didn't talk about this, so it won't be on your test, but length will shorten and mass will increase. I'd double check it's on your test. But the whole the whole time slowing down, we call that time dilation. And then the last but not least, I went ahead on the bottom here, wrote out kind of a low mass, what happens kind of as it lives its life, and then a high mass, what happens as it lives its life. So low mass is a protostar, then a main sequence, and then just giant. And in red I put it eventually will form carbon in its core, then a planetary nebula, white dwarf. And then the high mass, I said those first several steps are like basically the same for the high mass stars. But then it will continue fusing beyond helium into carbon. It'll fuse carbon into other stuff. And so a high mass star will go out with a bang, supernova explosion. And then we've talked about after the supernova explosion, it's going to leave either a neutron star or a black hole. And that's it.